Paul Wong, Senior Content Director with Electronic Design. Today we'll hear about designing systems that will operate within the desired temperature constraints, including some layout guidelines that engineers can follow.
My name is Dorian Brillet de Cande. I'm part of the application group at Texas Instruments. So today we're going to present you how to solve thermal challenges in your high power density designs. So first, let me present you the agenda and go through the different topic of today's presentation. We'll start to talk about the trends we see in most power designs driven by end equipment requirements and how it is making the evaluation of thermal challenges a priority. Then we will follow up with basic information regarding thermal management when it comes to power designs. We would like you to understand the parameters we're using in our datasheets and what do they relate to. Next, let's review together what you can do to make sure you're operating devices within their rated junction temperature, how to estimate the power dissipation, and what you can consider to improve the thermal parameters associated to your design. And eventually, we will compare a discrete device and its module version thermally. Let's dive right into this. Over the years, step-down converter modules solution size has been reduced for a 5-volt input, 6 amp output current from 278 millimeters square, as you can see on the left-hand side with the PTH module, down to 34 millimeters square with the latest low-profile TPSM 82866. And here you see also other implementations. So each implementation may have its own set of advantages depending on what end equipment they would be used in. Some power architecture would require flexibility in their design by adjusting the soft start, the output voltage, or operating mode during operation, or by getting information such as power or thermal good. Other design may need an extended operating temperature range to be designed in harsh environment and pass strict vibration and drop test. Pushing more power in overall smaller package size requires the power design to be more efficient, but above all, dissipate heat more efficiently through the PCB or through the package. A very similar story can be told for high voltage step-down converter modules with input voltages higher than 36 volt input, going from 901 millimeters square with the PTN module on the left-hand side of the screen and down to 120 millimeters square with the latest TPSM 63606. So as you can all imagine, we all benefit from shrinking systems and components, but it leads to high power density and therefore higher junction temperature. So achieving higher output power in smaller sizes implies a thorough investigation to evaluate the thermal capabilities of your application, including each and every devices on your PCB design. Extra care should be taken while assessing thermal parameters to evaluate your power design to be able to get most out of the power solution without exceeding its maximum recommended temperature. Thus, you can understand how much safety margin does the application have while operating at its maximum temperature. Power losses translate into heat. This heat is generated by the power dissipation, and the heat generation by the power dissipation will use different paths to leave the source. The primary heat transfer path of the IC will come from conduction. Convection on the other side will be the primary path for the heat to leave the PCB. And convection is really a combination of conduction and fluid flow. It allows heat to leave the PCB and travel to the ambient environment. And at last, radiation is what is measured by thermal cameras. Although significant, especially in smaller designs, much less heat is usually transferred as radiation. So our main goal here, while designing the power solution, is to provide minimum resistant path for the heat flow.